We'll start in 1 minute. We'll continue in section 8.2 today on the area of a surface of revolution. So we're still on the first page. Yesterday we derived a formula for an area of a surface of a revolution. So I'll write down what those formulas are. If we let y be equal to f of x, let that be a function that is positive, such that f prime is continuous, and rotating y equals f of x for values of x from a to b about the x-axis generates the surface area that's equal to the definite integral from a to b of 2 times pi times f of x times the square root of 1 plus the square of f prime of x dx. Two pi is a constant, so if you want, you can write the constant 2 pi outside of the integral. We can also use Leibniz notation if you prefer. So Leibniz notation for the surface area is the definite integral from a to b of 2 pi times y, since y is equal to f of x, multiplied by the square root of 1 plus the square of the derivative of y with respect to x dx. So this makes sense. As I mentioned, y is the same as f of x, and f prime of x is the derivative of y with respect to x. Okay, so our first exercise using the formula, find the surface area of a sphere with radius capital R. So any ideas on how to find the surface area of a sphere with radius capital R? Well, if we write down the standard equation of a circle with radius R centered at the point 0, 0, then that equation is x squared plus y squared equals capital R squared. This is just the standard equation of a circle centered at 0, 0 with radius R. If we solve this equation for y, so y squared equals capital R squared minus x squared, there are two solutions. Y equals positive and negative square root of R squared minus x squared. Each of those represents a half circle. The positive square root of r squared minus x squared. That represents the upper half circle centered at 0, 0 with radius r, and y equals negative square root of r squared minus x squared. That's the lower half circle. So if we just pick the upper half circle and sketch a graph of it, we don't really need a graph, but it might help. So pretend like this is a half circle. And the equation for that is y equals the positive square root of r squared minus x squared. If we rotate this half circle about the x-axis, then the solid that's produced is a sphere, and we can use the area of a surface of revolution formula to find the surface area of that sphere. Okay, so right up here we have that formula for the surface area. So y is the square root of r squared minus x squared. And we're going to also need to find the derivative of y and square it, add 1 to it, and put it inside the square root in the formula. So for now, let's find the derivative of y equals the square root of r squared minus x squared. So the derivative with respect to x, well, think of the square root of r squared minus x squared as r squared minus x squared to the 1/2 power. So I guess I can write that here so that we have something to look at. So r squared minus x squared to the 1/2. And when we take the derivative, we get 1/2 times the quantity r squared minus x squared to the negative 1/2, and then multiplied by the derivative of the expression on the inside with respect to x, which is negative 2x. And we can simplify this a little bit. 1/2 times negative 2x is negative x. R to the second minus x to the second to the negative 1/2 is equivalent to 1 over the square root of r squared minus x squared. So we can write this as negative x over the square root of r squared minus x squared. Okay, now we can start working on the formula for the surface area of the sphere. So we have S equals the definite integral from negative r to positive r, 2 pi times y. Y is the square root of r squared minus x squared. And then multiplied by the square root of 1 plus the derivative of y with respect to x squared. So we're going to square this derivative. When we square the numerator, square the term negative x, we get x squared. And in the denominator, when we square the square root of r squared minus x squared, we get r squared minus x squared. This is all inside the square root. Okay, and we'll simplify a little bit. On the inside of the square root on the right, let's find a common denominator and add the terms. Okay, the next line, we'll rewrite this stuff on the left. And inside the square root on the right, the common denominator is r squared minus x squared. So 1 over 1 becomes r squared minus x squared over r squared minus x squared. So we have an r squared minus x squared, and then plus the x squared that's already there. And in the numerator of the square root on the right, the minus x squared plus x squared adds up to 0. So some of you are probably already done. This is more detail than is necessary, but okay, so this becomes the square root of r squared over r squared minus x squared. I'll write it as a ratio of square roots, the square root of r squared in the numerator divided by the square root of r squared minus x squared in the denominator, dx. Hey, so what can we do now? Well, the square root of r squared minus x squared on the left, that's in the numerator, and we have a common square root of r squared minus x squared in the denominator. So those cancel each other out, and the square root of r squared is r. So this just becomes the definite integral of 2 pi times capital R dx from negative r to r. So we get 2 times pi times r times x, and evaluate that antiderivative between x equals negative r and positive r. And we're going to get 2 pi r times the quantity r minus negative r. R minus negative r is r plus r, or 2r. And 2 pi r times 2r is 4 pi times capital R squared. So you've probably seen that formula before for the surface area of a sphere. 4 pi times the radius squared. Okay, on the next page, find the area of the surface generated by rotating f of x equals the square root of x about the x-axis for values of x between 1 and 2. Just for convenience, I'll write down the surface area formula. Hey, we need to know what f prime of x is, so we might as well do that to start with. F prime of x, if f of x is the square root of x, f prime of x is 1 over 2 times the square root of x. So we also need to know what 1 plus the square of f prime of x is. So why don't we do that here? 1 plus the square of 1 over 2 times the square root of x. So here we just get 1 plus 1 over 4x. And since this is going to go inside the square root, it's usually an advantage to write this as a single rational expression with a common denominator. So 1 plus 1 over 4x is equivalent to 4x plus 1 all over 4x. Okay, so now we use the formula. Our integral will go from x equals 1 to 2. Don't know what that was all about. So 2 pi, and then f of x is the square root of x. And then inside the square root, we have 4x plus 1 over 4x dx. Okay, so how is this going to simplify? The square root on the right, we have the square root of the rational expression 4x plus 1 over 4x. So let's write it as a ratio of square roots, the square root of 4x plus 1 in the numerator and the square root of 4x in the denominator. So I'll rewrite 2 pi times the square root of x and the square root of 4x plus 1. When we simplify the square root of 4x, the square root of 4 is 2, so we have 2 outside of the square root, and then the square root of x. Hey, we get another nice cancellation. The square root of x from the numerator divided by the square root of x from the denominator equals 1. 2 pi divided by 2 is pi. So this becomes the definite integral of pi times the square root of 4x plus 1 dx from x equals 1 to x equals 2. Okay, what's the next step? Oh, we can use the substitution rule, 4x plus 1. So over here, I'll write u equals 4x plus 1. And so du is 4 dx. And so dx is 1/4 du. So we'll replace 4x plus 1 with u and dx with 1/4 du. We'll also change the limits of integration. Okay, so we're going to have a constant of 1/4. Pi is a constant, so I'll just bring the constant pi over 4 out front. And then instead of the square root of 4x plus 1, we have the square root of u. I'll write it as u to the 1/2, and then du. And what's the lower limit for this? How much?
6.
Yeah, 5. Let's see. When x is 1, u is 4 times 1 plus 1, or 5. And then the upper limit, when x is 2, u is 4 times 2 plus 1, or 9. Okay, so we get pi over 4. And then an antiderivative of u to the 1/2 is u to the 3/2 divided by 3/2. But division by 3/2 is equivalent to multiplying by 2/3. And then u to the 3/2. Evaluate this from 5 to 9. Pi over 4 times 2/3 is pi over 6. And 9 to the 3/2 is 27. And from that, we subtract 5 to the 3/2. 5 to the 3/2 simplifies to 5 times the square root of 5. Okay, so that is what I got for the surface area. Okay, the next problem. Find the area of the surface generated by rotating y equals x to the 3rd about the x-axis for values of x from 1 to 4. Okay, we need to know the derivative. So dy dx is 3x to the 2nd. And 1 plus the square of the derivative is 1 plus 9x to the 4th. This is what's going to go inside the square root. So our surface area is equal to the definite integral from x equals 1 to 4 of 2 pi times x to the 3rd times the square root of 1 plus 9x to the 4th dx. Okay, work on that for a couple of seconds, and online type in the result you get in a couple of minutes, or within a couple of minutes. How do you want to go about evaluating the definite integral? Yeah, the substitution rule looks like that's going to work. So if we let u be equal to 1 plus 9x to the fourth, then du is 36x to the third dx. In our integrand, we see x to the third dx. So we'll keep x to the third dx, and that's going to be replaced with 1 over 36 du. Okay, so let's make those substitutions. 2 times pi, instead of the square root of 1 plus 9x to the fourth, we have the square root of u. So I'll write that as u to the 1/2. Replace x to the third dx with 1 over 36 du. When x is 1, the u value is 1 plus 9 times 1 to the fourth, or 10. And when x is 4, the u value is 1 plus 9 times 4 to the fourth. So, hey, 4 to the fourth, how much is that? How much? Yeah, 256. And then 9 times 256 is 2560 minus 256. So 2304, right? And then plus 1 is 2305. Did I do that right? Okay, so 2 pi times 1 over 36 is pi over 18. So we can bring that out front, pi over 18. And then times the integral. U to the 1/2 du. So pi over 18. And then an antiderivative of u to the 1/2 is u to the 3/2 divided by 3/2, or 2/3 times u to the 3/2, from 10 to 2305. And pi over 18 times 2/3 is pi over 27. And for this one, let's just write 2305 to the 3/2, and then minus 10 to the 3/2. Okay, so that's the surface area. Okay, on the next page, okay, here's a restatement of the area of surface of revolution, but it's as it applies to rotating about the x-axis. So we'll go ahead and read this again. Let y equal f of x be a function that is positive, such that f prime is continuous. The surface area of the surface generated by rotating y equals f of x about the x-axis for values of x from a to b is given by this formula, or in Leibniz notation. Okay, but this is rotating about the x-axis. If we want to find the surface area generated by rotating y equals f of x about the y-axis for values of x from a to b, then we have to use this formula, the definite integral of 2 pi x times the square root of 1 plus the square of f prime of x dx from a to b. Okay, so if we're rotating about the y-axis, in the integrand, we're not using f of x, we're using x. So why do you suppose that is? Okay, I will attempt to explain the difference with a graph. So suppose we have y equals f of x on the interval from a to b. So the x-axis is the horizontal one, and the y-axis is the vertical one. When we rotate about the x-axis, rotate that once around the x-axis, the radius of the revolution about the x-axis, I'll give this, I'll refer to this x value as x star. The radius when we rotate y equals f of x about the x-axis at x star is the y value, which is f of x star. Seem to make sense? So when we're rotating about the x-axis, this f of x represents the radius of the revolution. Okay, but if we rotate about the y-axis instead, what's the radius of revolution in that case? Well, if we rotate this about the y-axis, that's the radius. And how long is it? X star is how long it is from the y-axis to that point. That's like from 0 to x star. So when we're rotating about the y-axis, the x value is the radius. Why does the square root of 1 plus the square of f prime of x remain the same? So what's that a remnant of? Or when we were discussing arc length, we had a definite integral of that square root. So you can think of it this way. If we rotate this about the x-axis, this curve has a specific arc length. But if we rotate the same thing about the y-axis, the arc length didn't change, right? It's still the same arc length. So the square root of 1 plus the square of f prime of x can be the same in both integrands. The only thing that's different is the radius. Okay, in other cases, you'll see x expressed as a function of y for values of y from c to d. And if we rotate this about the y-axis, then the surface area generated is the definite integral of 2 pi times g of y times the square root of 1 plus the derivative of x with respect to y squared dy. Okay, so this is the analogous formula to when we rotate f of x about the x-axis. Here we're rotating g of y about the y-axis. Okay, but we also have this case. If x is defined as a function of y on the y interval from c to d, and if this is rotated about the x-axis, then the radius, if we rotate about the x-axis, is the y value. Okay, so make sure that you apply the appropriate formula. So let's try an example. Okay, find the surface area by rotating y equals 1/3 times the quantity x squared plus 2 to the 3/2 for values of x between 1 and 2, and rotating about the y-axis. Okay, so for convenience, I'll write what we are doing and the formula that goes with it. So rotate y equals f of x about the y-axis. The surface area formula from x equals a to b, so the limits of integration are x values, and 2 pi, but instead of f of x, it's x, and then times the square root of 1 plus the square of f prime of x dx. Okay, so we have a function y. I could have written f of x equals 1/3 times x squared plus 2 to the 3/2. So just think of that as our f of x. We need to know the derivative. And so the derivative, 1/3 times 3/2 times x squared plus 2 to the 3/2 minus 1, which is 1/2, and then multiplied by the derivative of x squared plus 2, which is 2x. And we might as well simplify this a little bit more. 1/3 times 3/2 is 1/2, and 1/2 times 2x is x. So I'm going to write this as x times the quantity x squared plus 2 to the 1/2. Okay, we need to know what this is when we square it, so let's go ahead and square it. Okay, when we square it, square x, we get x squared. Square the square root of x squared plus 2, we get x squared plus 2. And then when we distribute multiplication by x squared, we get x to the 4th plus 2x squared. Okay, so now we can write the surface area integral from x equals 1 to x equals 2. 2 pi times x, because we're rotating about the y-axis. And then the square root of 1 plus the square of the derivative, so 1 plus x to the 4th plus 2x squared dx. Okay, what next? So we'll rewrite the expression inside the square root so that it's in the standard form, the square root of x to the 4th plus 2x squared plus 1. So do you recognize x to the 4th plus 2x squared plus 1 as something special? Yeah, it's a perfect square. If you square the quantity x squared plus 1, you get x to the 4th plus 2x squared plus 1. And the square root of a perfect square of something is just the something. I'll go ahead and write it in a couple of steps. So x to the 4th plus 2x squared plus 1 is x to the 2nd plus 1 squared. And so the square root of x squared plus 1 squared is x squared plus 1. So we end up with a pretty easy integral to evaluate. The constant 2 pi, I'll bring that out front. And our integrand is x to the 3rd plus x. And an antiderivative, x to the 4th over 4 plus x to the 2nd over 2, evaluated from 1 to 2. I'll leave the rest of that for you to do so that we can spend a little more time on the last example. This one set up the integral for finding the surface area generated by rotating y equals 1 over x for values of x greater than or equal to 1 about the x-axis. Okay, we're rotating about the x-axis. So our f of x is equal to 1 over x. And we need to know the derivative. The derivative of 1 over x is negative 1 over x squared. And then we're going to square that. So we get 1 over x to the 4th Okay, and our surface area formula. So the integrand, inside the integrand we write 2 pi times 1 over x times the square root of 1 plus 1 over x to the 4th dx. So what should I put for the limits of integration? Yeah, we're starting, x starts at 1, and then after that it's greater than 1. So it's an improper integral from 1 to infinity. That's how we interpret x greater than or equal to 1. Okay, so let's work on the integrand a little bit. Okay, so inside the square root, 1 plus 1 over x to the 4th, we can write that as a single rational expression. So the square root of x to the 4th plus 1 all over x to the 4th. And the square root of x to the 4th plus 1 over x to the 4th is the square root of x to the 4th plus 1. And in the denominator, the square root of x to the 4th is x to the 2nd. So the next step, the improper integral from 1 to infinity of 2 pi times the square root of x to the 4th plus 1 over x to the 3rd. This is an improper integral. First, let's see if we can determine if it converges or diverges. If it diverges, then we're done. If it converges, then we would like to know what it converges to. But any ideas on how to go about determining if it converges or diverges? Okay, let's try this. So the square root of x to the 4th, I'll go ahead and say the square root of x to the 4th plus 1 is greater than the square root of x to the 4th, which is x to the 2nd. Okay, if I multiply both sides by 1 over x to the 3rd, since x to the 3rd is positive, the inequalities remain the same, right? Or yes, the inequality is preserved. So on the left-hand side, divide this by x to the 3rd, and divide x to the 2nd by x to the 3rd. And x to the second over x to the third is 1 over x. Okay, I'm out of time, but we can use the comparison rule. We do know that the improper integral of 1 over x dx from 1 to infinity diverges. And since this integrand, the square root of x to the fourth plus 1 over x to the third, is greater than 1 over x, it also diverges by the comparison property. Okay, we're out of time. Go ahead and sign in for attendance.
Thank you.